Okay, let's get started with this week's series. This week we're taking a look at a couple of different ways to connect devices to your PyCon boards. So this is anything that could be sensors, LCD screens, literally anything you wanted to connect via a couple of different protocols. So the main purpose really of this stream is to show you how you can actually start doing things, for example, taking existing sensors, integrating them in MicroPython, and being able to start accessing sensors and devices on your PyCon kit. I'm going to focus on taking things like Arduino projects and being able to reverse them so that they're compatible with your PyCon board, taking libraries for sensors like accelerometers, LCD screens, rewriting them so that they work for not just Arduinos but also for MicroPython devices. It's going to be sort of a breakdown on taking existing code and rewriting it so that it works on the PyCon devices. The main things we're going to be looking at differentiations between how a library works in C versus how a library works in MicroPython, and also looking at some of the differences between the standard stream of MicroPython versus PyCon's version, with some discrepancies as to implementations, and this affects things like how different buses are called and some different variable names on functionalities. Things like the sleep library functions slightly differently, just some different naming. Some things like doing interrupts, that's slightly different as well. General purpose tips to rebuild libraries from X language, whether that's C, C++, Arduino, or Python, desktop Python, back into PyCon stream of MicroPython, PyCon version of MicroPython. So if we quickly jump into my overhead camera, we can see I've got a couple of sensors set up here. Okay, so I'll talk quickly about how I got them set up. That might help explain to what's going on. So just lower this down a bit and zoom in. Okay, right. So you can see what I've got here. I've got two different boards. I've got the expansion board, which is connected up via the I2C bus, to a breadboard, and that's got an accelerometer, an ADXL345 accelerometer, and then an LCD screen. And what we're going to be doing is we're going to be showing you how to talk to both these devices, how to import the libraries, and also walk you through how I rewrote them. So I'll give credit to the original author of the accelerometer library. That wasn't me, but I rewrote the Grove LCD RGB backlight library, and I'm going to walk you through the process that I went through rebuilding that library from. I actually took it from desktop Python, reversed it back into MicroPython, so there wasn't that many changes to make, but it was interesting because of some of the bugs that I pulled out that maybe weren't taking place on desktop Python but were taking place on MicroPython due to limited memory, and then explain how that process worked. So let me quickly show you how to actually start using these. So the general way libraries work in MicroPython is you have some standard libraries which you can import from the REPL. So that's things like import math, import I2C, import from machine I2C. These are importing libraries, all sorts of things like anything you want to do with time, intervals, anything you want to do with the ADC on board, anything that you can call directly from the REPL without having to upload code to the board. Those are your standard libraries. They're fine for your general connectivity, but when you want to start doing custom sensors and custom integrations, you're going to need to import some extra code. We're going to be doing this now. So I'm going to jump over to Atom and quickly show you how to do that. So let's bring Atom up again. Okay, so here I've got my Atom window. Now we've got right now blank file, nothing in it. We're going to open up our library to have a look at some examples. Okay, so let's have a look at the this library file. Okay, fantastic. So this library file originally was inherited from the I2C driver from Adafruit. I believe this was originally written in Arduino the Arduino version of C++, and reverse engineered back into MicroPython. So the original author for this this sensors library, or at least the MicroPython version, is someone named, I have it up here on Hackster because I've been following his project on Hackster. Let me open that up for you. Someone called, hopefully I get the pronunciation right here, Joachim Christensen, who rewrote a accelerometer library from Adafruit's breakout board back into MicroPython from C, and created a nice project explaining how to use Sigfox to send basically movement detection using this accelerometer. So he's got the board connected up in I2C, and then he's retrieving his data from a SciPy. So he did a nice write-up explaining about how he did that. If you want to find out more about that, if you go to hackster.io/PyCom, you'll be able to see all the projects on there, and you'll also be able to find out all the libraries and stuff that people have attached. So here's the library file that he's written up. I don't know if this is on GitHub yet, maybe somewhere. If not, I'll reach out and see if we can get it published so people can more easily find it. But then he grabs the library and then imports it from his main.py file. What you need to do in order to get a library on your device is you actually need to upload the file first. So what you do is you download this ADXL library, and then you upload it to the board either using FTP or even the Atom plugin. This way, the board has it on reference, so you can actually import the library. Not all of the libraries that we're referring to are standard libraries, such as this one, so you do need to actually upload them to the device. So let's go through the process of doing that now. So I'm going to do this through FileZilla, just because you can see exactly where I'm putting the file, and it'll make sense as to what I'm doing. So if I quickly open up and check what the IP address on my, I'm using a LowPy here today, what the IP address on my LowPy is, I can see that it is here. So grab that quickly, and let's jump back over into FileZilla, and let's upload that to the device. So I think we might already be connected to it. Yep. So connect, start a connection. So once you're into your board, once you've connected over, let me make that a bit bigger for you. Once you've connected over, you'll be able to see the file directory, jump into Flash, and then, so here I've just got some extra stuff on the board, so don't worry about demo, that was just from another project I was doing. But you'll have your main.py, your boot.py, .sys, .lib, and .cert. We want the .lib folder, so if you open that up, you'll see that I've already got some libraries in here already from when I was previously preparing the demo. But what you would want to do is you go over to the left-hand panel, find your project. So in this case, under libraries, I have the AXDL library, and then I'd open up that lib file, grab the ADXL 345, grab that, copy it over, and drop it. So mine's already on board, so don't have to worry about copy and pasting that. But once you put it into the .lib file, once you do import the library name, your board will know where to reference that and be able to find it within the library for you. Okay, so let's jump into the terminal and actually have a look at the REPL and see how we can import that library. So let me pop back over to Atom again. Okay, so we're in the library. We can run import ADXL345, and hopefully that library's in the right place, and the board should find it. Perfect. So that was successful. So we now have access to that library. So what we want to do now is let's have a look at the library and see how this is set up. Okay, so just having a look at the library information, we know that it's grabbing an I2C connection and then creating an object around that with some standard values as well. So when you call the library, it will initiate this initialization method and set up the library as per how the author of the library has dictated here. And we can see that they're using a bandwidth rate of 100 Hertz with a range of 8G, and they're enabling the measurement on the board. So let's quickly try that out. So let's create a library file. Let me just quickly check that we've got no comments going on. Okay, one plus is the string at least. Okay, so let's create an object. So ADX is equal to ADXL, and then we know that the class name is also ADXL, so we want to rename the file for consistency's sake if we're actually doing it. And then we can pass in, actually no, first of all, so we do actually need to set the I2C bus quickly first. So as we said, the library does use I2C, so let's do that now. So we can do from machine import I2C. Now we've got an I2C connection, so we need to create an I2C object to pass into our accelerometer class. So let's do that. I2C is equal to I2C dot master. So what we're doing here on the board is we're just using the default pins. I'll quickly jump back over to my camera to show you that. So you can see what I've got set up here. I2C I'll touch a little bit on, but if you're interested, you might want to have a read up. There's some really good tutorials online about how it works. But basically, it's a two-wire protocol that allows you to address a number of sensors all connected up on these two wires. You've got a clock and then your data line. So your clock line is normally specified by SCL. So you can see here, these are the yellow wires are specifying the clock line. And then you've got your data line as well, which is, in this case, a bit confusingly, the white and green wires because it didn't have a spare white jumper lead. But the way that this works is when you send over a message to the board, what you need to do is you need to first specify the address of the device on the bus, and then you can specify either the register that it wants to go to, and then the specific value you want to put in the register, or you can arbitrarily specify that you want to send X value to this address, and then hopefully that device will know where to put the that piece of data or memory that you've sent over to it. And we can have a look at the library as to where those things are being sent to and how it's doing that. So back into Atom again. Okay, so we've created the I2C connection, and these are using the default bus pins for the low pi, and I believe this is the same for the Y pi and Sci pi as well. So these are pins G17, G16 if you're using the expansion board, and I believe that's pins P10 and P11 or P9, so whichever one's the equivalent of the expansion board pins. So these are just the standard pins. You can specify if you want to use custom pins. If you're already using it for something else, you may want to change it. But these are the default pins that I'm using today. So we've now got our I2C library set up. What we can do is a quick scan to see what actually is on the bus itself. So this returns all of the devices that are connected and all their addresses. So we can see that we've got 3 devices. So I know just from having worked with these libraries before that the LCD screen actually creates 3 different addresses. And then the accelerometer just has the one. So I believe 83 is the accelerometer, 62, 98, and 111 are to do with the LCD screen. And these are actually the decimal equivalents of the hexadecimal values, hexadecimal addresses that are stored in the devices. So we can quickly check to see actually if that device has the right address. You can see here, so x53, if you change x53 from hexadecimal to decimal, you'll be able to see that that goes to what I believe is 83. I'll try and do that in my head really quickly. Someone can correct me if I'm wrong. Okay, so we created that I2C connection, and now we can go back to the accelerometer. So let's jump into that. So we can do ADX, like we started to do earlier, is equal to ADX.ADX, and then pass in our I2C object. So we've done that now. So we've now created an object on the I2C bus, and then we created an object within the accelerometer class for this specific accelerometer, or specific connection on the accelerometer. So then we can have a look at the library and see what we can actually start calling to get information back from it. So we know that the library initiated, set up the address, set up the bandwidth rate, set up the range, and enable measurement. It looks like there's a couple of different functions in here. So getAxis is the main function here, and basically what this is returning is all of the values to do with the XYZ coordinates of the device itself. So let's do that quickly. Let's do ADX.getAxis, and then let's set that to true. Okay, so that returns some values for us. So let's try tilting the board over. So let me see if I can split my screens here to show you what I'm doing in both windows. Okay, let's get the hover cam up. Okay, ooh, so that looks like it's all over the place a little bit. Let me hide FileZilla, hide Chrome, and bring back up Atom again. Let's put hover cam on top. Okay, so we've got the hover cam now looking at the accelerometer, and you can see at the bottom of my screen I am calling the function or the method on the accelerometer class and getting values from the board. So if we then tilt it up, we tilt the device up, we should get some different readings on it. So yeah, you can see the z-axis has changed, the y-axis has changed, and the x-axis has relatively stayed the same, although I'm probably moving it a little bit with my hand as I lift it up. Okay, so you can see that's how we've used the library. So this was very generously written by one of the members of our community. I think this is relatively lightweight. It's not calling a lot of functionality from this specific chip, but I'm sure with time this will get built out and you'll be able to do far more with the library and actually probably optimize it a little bit more as well. Okay, so let's just see if we've got questions going along. Okay, we're all good for the moment. So let's talk about discrepancies now as to how you go between an Arduino library to a MicroPython library, from a MicroPython library specifically to a PyCon MicroPython library. Okay, so to do this, let's jump into Chrome. So look at my browser and we'll have a look to see actually about library specifics. Okay, so let's take the Grove LCD screen that I was using earlier. So this is the screen that I rewrote to work for PyCon boards. Fairly standard. It's an I2C LCD. I was going to do an example today with SPI, but I thought doing SPI and I2C in the same video might get a bit complicated, so I'll leave that for another video and probably talk about that in a couple of weeks' time, talk about different protocols and why you want to use one versus the other. Just sort of a brief overview as to different connectivity options on our boards and how you can do things like UART, I2C, SPI, and the various different interface protocols. So this is a RGB LED, meaning you can change the backlight, you can display characters on it, custom text, you name it. This is from Seed Studios. It's a pretty standard module. There's a lot of different functionality available on it, and it's quite well documented as well. So when I started working on this library, I found two equivalent libraries. There was one written in C, which is actually written by Seed Studios themselves. So this is, let's have a look at that library pretty quickly. So this is written in Arduino C++. Arduino is basically effectively what's a wrapper for C++ to reduce some of the complexity, to make it a bit easier to understand. But you can see this is the main bulk of their library. So if you're familiar from Arduino, this should look pretty standard. If not, don't worry, bear with me. C is a little bit more complicated to understand, less readable than MicroPython and what we're working at the moment. But generally, the concepts are the same. So they're doing a similar thing here, importing libraries, grabbing them, and then using those libraries to actually construct their own library. They have to specify a little bit more detail than what we used to because we have access to lovely Python libraries, which simplify everything, as opposed to C++, which ends up being a bit messy and complicated. So they have to actually do a lot more low-level interaction than what we necessarily have to do. So they are specifying here about sending a byte over the I2C bus, so specifying the address, the data, and the network transmission. So that for us would be equivalent to, let me get up my version of our library, or the MicroPython library. Okay, I'll open a couple of these up in Atom. Okay, just keep me a second while I open these up. Okay, so let me jump back into Atom. So you can see my library here, what I'm doing. So when we created the I2C bus, we just created an object like we did in the Accelerometer library. And then when we want to write to things, we actually do it in a level lower. So let's look at the screen library and see our write functionality. So, okay, for example, here we are writing a character into the memory of what's on the LCD. we simply call this write to memory function and don't worry about what happens below. When you do it in Arduino, it's much more complicated. You actually have to go into and dive down to a low level to specify data transmission, specify exactly where you want it to go, whereas we can just pass that all in with one simple, easy function. Okay, so let's go back to Chrome and quickly have a look at what's going on again. So they've got a function for sending a single byte, function for sending multiple bytes, a constructor for their library object or class, and then they start specifying the methods within that class. So this is the setup functionality where they go through specifying all of the details about setup. I won't dive into this too much. You can have a look at my library if you're interested in the specifics. But these basically have to do with the datasheet of the LCD itself and as to powering on and when you're supposed to start sending data to it, as opposed to just arbitrarily firing data across to it. I think there's a power cycle. You've got to wait something like, I think they specify here, you can wait 40 milliseconds before sending commands to the device. So they just handle all of the specifics according to the datasheet. So the specific IC that they're using for this LCD screen is the HD44780. And again, if you want to look more into specific low-level details about actually building up from the datasheet, which I won't get into today because it'll take a bit longer to actually do a datasheet integration, you can start building up and seeing what information you can send to the device's specific registers to get specific functionality. So you might want to do this, for example, to amplify the accelerometer, or you might want to use it to find out specifics on maybe this LCD. So they set up the device, then they start looking at doing the commands for various things like clearing the display. So there's the function for that, returning the cursor to home, setting the cursor to a specific location, doing things like turning the display on and off, changing the cursor over, etc., etc. There's a lot of functionality in this library that enables users to do a lot of different things. So heading back over to Atom again, we can see where we do this stuff. So the way that I've written this library is I've actually chosen to split it up a little bit more to make it easier to understand from somebody who's trying to actually learn about how the library itself works. So what we've done is, you might remember I spoke earlier about how the LCD screen has a number of different addresses. Well, the reason to do this is because actually the backlight and the screen with the characters displayed on it are actually separately addressable. So you could control the two of them independently of one of each other. And we actually do that within this library. So we've got one upper level, and then beneath that we have the screen specific to do with characters, and then we also have the backlight as well. So what we do is we call those two objects into the upper level, which is what we interface with. So here we import the I2C LCD backlight, the I2C LCD screen itself, and then we create objects within those from our specifics here. And then we bring out all of those objects to the class, so you can call everything from an upper level. You just need to call the I2C LCD, and then you have access to controlling both the screen and the backlight. Okay, so let's look at the screen itself to actually put cursors on the screen. So we first start off by specifically declaring all of these different values for functionalities. So these are the specific flags for different things like just moving the display, moving the cursor, blinking the cursor, changing different characters, clearing the display, so on and so forth. And then there's also in here some of the addresses as to where that information should be sent. So for example, setting the clear display functionality goes to a specific address, specifying that the LCD is in 8-bit mode, that's also another value to be sent to a specific address. And you can see within inside the library how we actually do that. So we've got a command function which handles that. Basically takes our command which we pass to it, whether it's, for example, let's say, set the cursor. So here we use the cursor method, pass in that specific value that's referenced at the top of the library, and do some control on that as well as to what we're actually trying to do with it. So let's look at the equivalent now from Arduino for setting the cursor. Okay, that's Robin. You can hear me, is that correct? It's not just that you specifically don't have sound. I think the microphone should be coming through fine, so just let me know if you can't hear me for any reason. Okay, looking at the cursor in the library, so let's have a look at what that is. Let's do a quick search, just to be easier. Cursor. Okay, set cursor. So what they're doing here is similar to what we do in our library. They specify a column and row, which is a unsigned integer of 8 bits, passed it into the function that's within inside of the RGB LCD class, and then they do some bit manipulation magic to actually get you a column and row out of that specific information you pass into it. And then they send that data, which is specified here by the unsigned character array, DTA, and then send those bytes over the I2C bus using the function at the top of the library, and specify the length and data sent to the LCD address. So it's pretty similar. We just do a check here where we say row, column, do our bit manipulation magic. It's a lot simpler in MicroPython because you don't have to specify the object sizes and types. MicroPython is clever enough to handle that for you. Makes our life a little bit easier, just removing some of the complication as to what you're actually doing. And then we do, once we've got the column value set, we send that over our command function, which is up here, which says just check that the command is valid. It wraps it as a byte array, which means that it's being sent over as a bit value, then being sent to the address of the I2C, and then the LCD address, the screen address specifically. So this is a register within the I2C bus. What we do briefly here, this is a bug that I was finding with the library. So actually we send a blank value to it first, make sure that it's empty, and then we write a command to it. So this just ensures that there's no overflow issues or anything with data being rewritten to the same register multiple times and causing issues. I was having the LCD crash sometimes when I was doing that, so passing an empty value to it first just to make sure it's clear, and then we pass that command. So I think this might add a little bit of latency to it, but it's basically you can't notice any difference. Okay, right. So you can kind of see the difference now between Arduino and MicroPython. So what I would recommend doing if you're actually interested in rewriting an Arduino library to MicroPython to our specific flavor of MicroPython, I'd actually take a look at the library I've got here, the I2C library for the LCD screen, and then take a look at the Arduino, put them side by side, sort of scroll through, look at discrepancies, and see what you might need to change to add over. You normally probably want to do this with the datasheet in front of you as well, so you can go through and check the registers. This stuff can get quite complicated, so you might be good to sit down with a couple of hours to spare to start comparing and checking values, making sure that everything's working correctly. And one of the best things that I find for doing this actually is to do it in the REPL. So when you first start working with testing things out and seeing get them to work, use the REPL to do it on the fly. So one of the things that always used to frustrate me about Arduino development or C++ development was that every time I wanted to try and change something to my code, I had to reflash the device. That's not the case here. You can just jump into the REPL, try a bit of code out, and see if it works. So let's have a look at actually importing the I2C library, and then we can show you it doing some stuff on the hovercam, just to show you that what I've written does actually work. So let's import that. So import I2C LCD. Okay, so we've got that library. And then we can also pass the same I2C object that we had earlier we were using for the accelerometer. So we can do, let's just call it D for display is equal to I2C LCD. Let's have a look what we've got in there. So we want to set up a display. So the class is called display. Then we want to pass in the I2C bus and create our object. So within here, we already know specifically, if you look at the upper level, you can see that the LCD address is set to a hexadecimal value of 3E. Obviously, if this changes for you, you can specify it specifically as passing into parameter. So if you wanted to put it on a different address, you could do that. Some LCD screens I know have pins on the back that you can change the headers for, or you can solder them to specify specific address buses. If you want to do that, you could just change it. Here we've got the LCD address specified and the RGB LCD, so that finds it for us perfectly fine. It just needs the I2C object to be passed in. Okay, so we've got our object created now. So D is an I2C object, and now we have all of these methods that I've written available to us. So we can write to display, set the cursor state whether it's there or not. We can blink it. We can blink the LED. We can auto scroll, set display, change the color. Sorry, clear display, set the home, change the color, and move the device. So let's quickly write something to display and show you. So let me get back the hover cam on top. Okay, so let's zoom in specifically on the screen itself. Okay. Right. So we've got the screen here now. Here's everything connected in, powered on, hopefully. Let's do a double check that all our connections are still attached. So it looks like it's gone to sleep for some reason. Okay, perfect. So the screen has initialized. You can see if I just focus in quickly there. Perfect. Okay, brilliant. So you can see that the screen's initialized with some blank characters on it. So what we need to do actually is probably clear that. So we can do d.clear. You can see Atom I'm typing in. And perfect, so that should have cleared the display, although it looks like it's not actually cleared. I wonder if we've got this wired up quickly. Let's just do a quick double check. So SCL, wired in correctly, perfect, perfect. Okay, interestingly enough, let's just write a character to it, see if that's working. I may have done something silly here. Okay, so it looks like something interesting is going on. Let's try and work out what is happening here with the screen. So we've got it plugged in. That should be fine. So it's powered. If we disconnect power from it, it should unpower. Okay. We've got the ground connected. We've got the data line connected as well. Yep. Okay. Let's just go straight from, let's take out our accelerometers, make sure that's not causing any problems, and go straight into the board itself. This will just reduce any of the issues that I'm having on board at the moment. Okay, so into the correct pins. And let's give our local a quick restart just to make sure. Okay, brilliant. So we're in. So let's import our library. Import I2C LCD from machine import I2C. I2C is equal to I2C. I'm master. Perfect. Okay, and then we can do let's call D again is equal to I2C LED dot display, passing our object in. But oh, okay, so we got a bus error. Let's do scan. I2C dot scan. Oh, okay, so this is interesting. It says there's nothing appear on the I2C bus. Let's debug, see what is going on here. Right, so let's get up my datasheet quickly for the load time and have a look. This is good actually. This will show you some of the debugging steps as well involved with. So I handily have a printed out version of the datasheet. We can see here that the clock line is specified as P10, which is GPIO 13, and the SDA, which is the data line, is P9, specified as GPIO 12. What it looks like from my device is that so we said that the clock line is yellow. Looks like we've got the clock line and Z line the wrong way around. So we should be able to easily debug this by swapping those two around. So yellow first and then green, which is I think what was happening earlier actually as well. Okay, just try that. Perfect. And then we'll try to call our constructor again and see this time if the LCD screen works. Okay. So let's do scan. Okay, perfect. It's found the bus now. And now let's look at the display itself. Okay, perfect. So it's clear display and looks like our function has worked. So success. The issue there was the I2C connections were the wrong way around. Perfect. So now we can start writing stuff to the display. So d.write hello YouTube. Perfect. Okay, so we've got characters printed in the display, and this is using our write function from our library here. And if we dive down into screen.write, let's have a look at what's going on there. So in write, we're taking a character in our text, which is our string we passed into it, doing our write character. Write character here checks that it's a valid character, wraps it in a byte array, and then passes it to the character address, well, character register within the address of the screen. And this then in turn prints out on the display. So we can clear that, so d.clear to get rid of our message. Boom. So it's gone now. We can do things like control the backlight, so let's do some backlight stuff. So d.color. Did I spell this like the English way? Nope, spelled the American way. Don't know why I did that. Okay, so we can see in here, let's have a look at the library. So they want an R, G, and B value. So these are between 0 and 255 to specify the brightness of the color. So we can do, let's say, let's get red. So 255, 0, 0, and we should have a red LCD. We can then write characters on top of that as well. So d.write. Okay, so we can write to the screen, and then you can do a whole bunch of other different things. So let's change it to another color, d.color. Let's change it to maybe a mixture of something. So we could go like full white, so 255, 255, 255. We just have a white display. So this is a fun little library for an external device. I've used this for a number of projects. It's really easy once you've got the library running to start integrating stuff. And the whole point of libraries is to make it easier for you to abstract away complications in the actual functionality of the device. So imagine if you had to rebuild this every time you wanted to write code for the LCD. You had to rewrite the same code, copy and paste in your code. It would just be an absolute pain. Whereas if you create a library and create a callable class that you can then import, it makes life a lot easier for doing interesting things like bigger projects and other things. Ooh, sorry, okay, got a question here. I'm in a bit of a break, so I can take this question now. How do I do the FTP again? Okay, I'll quickly mention about that. So I've assumed a little bit of background knowledge here. So what we've got running on the board is in the boot up script, I have it set up to open a network connection. So you can see here, I'm connecting to our office connection and then just printing out the IP address. So I'll have a look at our boot script quickly, although I might have to come back to that. Well, actually, what I suggest, I'm going to link you to a comment below afterwards with a link to the forums and how to set up a custom network connection, because otherwise I've got to go through and blur out or to change our credentials for our personal network. So we'll get back to that at the end. But basically what I'm doing is I'm connecting to my home network or the office network here, and then in FileZilla, I'll move over to FileZilla, and I'm then basically going into that and let's have a look at that. Bear with me a second. So what I'm doing with that is I then go to my host, plugging in the address that it created, the IP address, so it was dynamically connected with the device connected to the network, and then connecting to it, which then gives me the whole list of everything inside of it. Okay, so back to what we were doing. So you can do a number of different things with this LCD screen. And yeah, as I said, the whole point of libraries and creating classes for these things is to make it easier for yourself later down the line when you want to implement things, when you want to change things and do things. I have a number of different devices I've written libraries for, mainly to be honest, to help me write documentation, tutorials. So libraries for doing, for example, we've got a couple of sensors in the office doing things like temperature monitoring. So one of them is the one-wire protocol, which I've got a video coming out shortly about, so you'll be able to find out about that in that specific video. But again, that's another different protocol, which is intended again to use one wire to communicate with, as opposed to two wires like I2C or four wires like SPI. So you can see now why we do this kind of thing. It's to reduce the overhead and to make it simpler for us. And the nice thing as well is that as the community grows and starts producing more and more content and libraries for different devices, it means that it's easier for you to quickly just search on Google or GitHub for the specific name of your chip, and then 9 times out of 10 you'll likely find a library for it. So let's do that now actually and have a look at some of the differences between MicroPython for some devices versus MicroPython for the PyCon devices. So there's a couple of different things that are different, but generally the discrepancies are small, so you need to change one line of code or 2 lines of code to get things to work. Okay, let's have a look at some MicroPython. So let's have a look at one of the Adafruit libraries, because they've got quite a lot of good libraries. But again, there's work on CircuitPython, which is their branch of MicroPython, so you need to change a couple of different lines of code to get their sensors to work with our boards. Let's have a look. Okay, let's find a nice MicroPython library. Maybe search more specifically MicroPython. Okay, let's look for MicroPython. What should we have a look at? Let's have a look at this OLED. No. That's probably a little bit too specific. Maybe this would be the one, RGB pixel display. Let's have a look. Let's see if they have anything different so I can point out to you to look out for and be aware of. So generally, the devices function differently, mainly due to the architecture of the microcontroller that the board is running. So with all of the PyCon devices, they run on ESP32. So it means if you write any code for any of our YPy 2.0, LowPy, SciPy, it'll all work the same. They all use the same processor. So there shouldn't be any problem there. The only difference would be if you're using a MicroPython library for a different device, such as like the STM32 or trying to think of other devices, other MCUs. There's a whole range of them. You can check out the MicroPython repo to see which other devices there are. But generally, they'll run slightly differently to how they do on the ESP32. So let's take a look at the library. Okay. So bear with me because this is the first time I've seen this library. I'm looking for differences. Okay, so right. Okay, here. So this is interesting. So with MicroPython, the way that you refer to pins and you actually specify, so this is just GPIO pins, so general purpose input output pins. They're actually toggled in a different manner. So what is happening here is that, let me see where they're actually setting pins up. So where do they initialize the pins? Hang on. Okay, so they're getting the SPI pins. So they're clock select, chip select, SPI bus, reset pins. They're importing. Did they actually set them up here? They just pass this guy in. So let's have a look, see if they have an example. It'll be clearer in the actual implementation example. Hopefully they have one. Maybe some documentation. So SPI, for example, is one of the interesting things that works slightly differently. So let's get up the MicroPython repository and see how classic MicroPython does it versus how we do it on the Python boards. Okay, so let's look at our library for SPI, see how that's set up for us versus classic MicroPython. Okay, so when you want to set up SPI for us, basically you pass in, say, from machine import SPI, then you create your object with your specific values on there, like that. So there's a couple different ways you can set up the object. This is imported from machine library, machine class, and then you can create an SPI object. Let's look at MicroPython now, so documentation. And this varies for a number of things. So generally it's to do with interfacing, so different protocols, also the sleep functionality, so if you're doing anything with timing, that generally works a bit differently. It's not that they function differently, it's that you create objects and instantiate slightly differently. So classically, with MicroPython on the PyBoard, you'd call the PYB library. We instead call machine. I think that's actually been updated now in the official MicroPython branch to use machine instead of PYB. But previously you used PYB, so you might find libraries still referring to things like that. So just be aware that the equivalent for PYB on current MicroPython is machine. But then the constructor is pretty much the same, but we don't, I believe, support yet for, maybe we do specify CRC. No, we don't yet specify CRC yet. So again, something's just slightly different, but it's worth checking to see where the library came from because there will be differences. And then obviously as well, there's some different ways that you call the class. So we have some different names things. So SPI write, SPI read, as opposed to MicroPython, which is, or classic MicroPython, which is SPI receive instead of read. They have send as well instead of write. So we generally in our branch of MicroPython refer to any of the outgoing transmissions as write and any of the incoming as read, whereas classically I think MicroPython generally refers to it as receive and send. And again, so this is send receive. I think we have a oh no, so we don't. Instead, we don't have a read and write. We have sorry, write and then read. We instead just call these different methods individually. And then there's specific constants that you can call as well. So we have much the same, but we're still building out our library. So some support for some things like being able to use it as a slave device aren't necessarily supported yet. And also some of the different functionality like setting the LSB isn't there yet. But these are all things that are coming, and I wouldn't be surprised if some changes take place later on to make it more compatible between the two. Okay, so let's do an overcap of what we spoke about today. So we did a quick example importing libraries onto the board to show you actually how to upload the correct file and then refer to it. So this was specifically for a sensor, but this could be for anything. This could be MQTT, this could be HTTP requests, anything that's not supported in the standard library you need to upload to the board via FTP or the PyCom PyMaker plugin. We also then looked at how to call that library from the REPL. So the REPL will be the same as actually referring to it in your script. You do the import, name of your library, and then you need to specify the specific class that you're going to create an object from. We then had a look at the different devices we've got connected on the I2C bus. So the I2C is a 2-wire protocol connecting a number of different sensors. So here we had an accelerometer and an LCD screen. We scanned the bus to see which devices have appeared on there. So this are the addresses for the specific devices. We then looked at how a MicroPython library was constructed with the classes of objects being called. We then looked at how to call the methods on those objects and be able to actually control them. So we looked at the LCD screen, how to control the screen itself, how to control the backlight, and how they were both wrapped up in a higher level libraries to add interface and control directly through that one library rather than controlling 2 separate libraries. We then looked at some of the differences between MicroPython and Arduino. So again, this kind of gets a bit detailed because there's a lot of specifics that are specified more thoroughly in C because it's a lower level language. You need to be more specific as to the sizes of the data structures you implement. You need to be more specific as to variable names and types. Whereas in MicroPython, it's a lot more freeform. You have a lot more flexibility with not having to specify everything. MicroPython is very good at handling that. But again, like there's trade-offs as to having that control. Generally, MicroPython is very, very good at doing it, but there might be some cases where you need to have more control than MicroPython allows you to, and maybe you're in a more memory-constrained environment, which generally isn't the case for ESP32. We've got a lot of memory available to run MicroPython scripts, but if you were running on, say, another device with more constraints, you might be better off doing a C library. And then we looked at controlling the screen itself, so calling the methods on the class, actually importing them, and then using them. So this is like writing to the screen, clearing the screen, changing the color, instantiating it, etc., etc. And again, if you're writing your own libraries, you'll need to check the datasheet to make sure you've got a specific set and that everything's correct. And again, this can be quite an arduous process. So what I would do is sit down with the datasheet and your device and your editor, code editor, and take some time to actually work out what's going on and how to go about implementing. And then finally, we had a look at the differences between MicroPython, classic MicroPython, and then the Python version. So generally, these aren't to do with Python itself. The underlying Python is the same. It's just the classes and libraries that generally vary. So these are specifically for things like protocols, so SPI, I2C, maybe the ADC, the DAC on board as well, and some of the timing libraries as well. So just be aware that if you're implementing a MicroPython library for a different device other than the ESP32, other than a PyCon board, you may need to write some changes to just call different methods and functions by different names. So that's pretty much it for me. I'm going to probably dive into some more sensor stuff at a later date. But if you want to let me know in the forums on my post about what you'd like to see next, I'm happy to do different suggestions. I rescheduled the event for doing a community showcase. I want to showcase some of the projects we're doing because there's some really interesting stuff going on. I'm going to probably reach out to a couple of people who spoke to me, who actually reached out to me, and try to find a date. It's a bit of a pain trying to schedule it in the middle of the day, though, because I understand that everyone's doing their jobs and can't necessarily take an hour out of their time to come and jump on a Skype call to talk about their projects, their personal projects. So might end up having to schedule it for maybe a weekend or something, just take an hour or two to have a chat with some of the community and see what they're doing. I'd like to talk to some people who are doing interesting things with LoRa, some people are doing interesting things with Sigfox, and some people who are doing interesting stuff with just different sensors and different embedded applications. So exciting to see what happens there. I'll probably do some videos as well coming up with the PySense and PyTrack that should be arriving shortly. I think there was a minor delay with them, but they should be out soon. So it'd be interesting to see once they arrive if we can start doing some tutorials and some information about them. Maybe we have some fun projects we can actually do, taking it out into the real world and doing some GPS tracking and some other stuff. So if you have any questions, let me know quickly. Otherwise, we'll wrap up and see you all in 2 weeks' time for the next live stream. So it doesn't look like anyone's got anything to post. I'll give it a couple more seconds. If you're interested in looking at existing sensors and some of the MicroPython libraries that have been written already, you can actually check out, if you head to the PyCon organization on GitHub, you'll see that there are some libraries available already. So this actually needs to be updated. We have some stuff that's, that needs to be uploaded into this. generally they're pretty good. So these are referring generally to things like MQTT. There's some stuff in there with the one-wire sensors. So we want just PyCon. So if you go to PyCon, and then you go to PyCon-libraries. So you'll see in a second. PyCon-libraries. So our libraries both have examples and also the library source code as well. So everything you'll need to set it up. So this also includes things like our LoRa gateway stuff and Nano gateway libraries. Yeah, for example, say let's have a look at an example using the ADC. So inside our main library, okay, this is less relevant because it's a standard library importing it from machine, which is a standard library. But examples for how to use that as well are in there. Let's have a look at one you have to import. So let's check out. Let's just have a look at MQTT. I know I did MQTT a while back, but it's the same concept. So you have the MQTT file here, and that has all of the information as to how that library specifically works. So you obviously drag that file, put it into your library folder, and then you'll be able to use it from there. Okay, so that's basically it. Doesn't leave any questions, so we'll leave it for this week, and then rejoin again in 2 weeks' time for another webinar. And do let me know what you'd like to see, because these sessions are all dictated by the community. It's all about what we can do to help you out, to help you get started with your projects, and to make it easier for you to develop whatever it is that you're working on. Okay, so see you in 2 weeks. Goodbye.